This is what the inside of an Airpod looks like. A tightly packed wonder of modern electronic engineering, every piece fitting neatly together like a 3D puzzle. The battery, the speaker, the Bluetooth antenna, all carefully packed into a space not much bigger than your fingertip. A technology that would have seemed completely far-fetched just 10 years before its introduction. But getting everything to work in something this small took years of engineering. Every curve, every connector, every sensor had to be designed to fit and function perfectly within this tiny space. When you scan the inside, you're not just seeing parts, you're seeing what's possible in consumer electronics today, a triumph of miniaturization. So, let's take a closer look at each of these components and break down what they do, why they're shaped the way they are, and how they all work together to bring the Airpod to life. This is a CT scan of a second-generation Airpod Pro, with the volumetric data provided to us by LumaField. We have developed a workflow to take this data into our animation software to give you a peek inside this modern marvel of engineering. Like in medical imaging, X-rays pass through the device from multiple angles, and a computer builds a 3D model based on how much radiation each part absorbs. Up here at the top, you can see the speaker, tucked into the part that sits right inside your ear. Right behind the speaker is a small cylindrical cell. This is a 182 mAh lithium-ion battery, about 2% of the battery capacity of an iPhone. The crazy thing is, that was enough to give each AirPod up to 6 hours of use. That 182 mAh is held in a battery that weighs just 3 grams, which works out to around 60 watt-hours per kilogram. Not particularly impressive, but Apple's consistency in manufacturing really shows up under these CT scans. If you look at the scan, you will see a layered structure. This is the battery core. On one side is the cathode, and on the other, the anode, and in between is the electrolyte. During charging, lithium ions move from the cathode to the anode and get stored there. When you use your AirPods, these ions flow back, generating electricity. The battery is built like a rolled-up scroll with layers of material wrapped tightly around each other. That tight packing really matters. If you look at a fake AirPod or a cheap knockoff, you will usually see the battery is not nearly as compact. Gaps between the electrodes, sloppy layering, less control over how everything is placed. And that has a direct impact on battery life. Poor packing means less active material and fewer lithium ions moving between each cycle. That reduces energy density and increases internal resistance, so more energy is lost as heat and the battery wears out faster. Here in the scan of the charging case, there is a faded patch in the corner. That is where the electrolyte has broken down. It is no longer making contact with the electrodes, so ions cannot move through that region. This is literally a dead zone in the battery. These zones can form when you move your AirPods from a warm room to the cold outdoors, or if you accidentally drop them on the pavement. These sudden changes in temperature or physical shocks can stress the battery's internal layers and start breaking them down. And it's one of the reasons your AirPods might start out with 6 hours of battery life, but after a year, the battery life decreases to only 2 or 3. Behind the battery, you'll find the AirPod's core component, the Bluetooth chip. Bluetooth technology kind of flies under the radar for how amazing it is. There is a reason why so many different wireless technologies use this strangely named wireless data transfer system. In the early 1990s, engineers were trying to figure out how to get devices to communicate wirelessly without running into constant interference. Bluetooth uses radio waves in the 2.4 GHz range. This range is great because it does not require a special license to use, making it accessible for all kinds of consumer devices worldwide. It also has a good range and can pass through walls reasonably well compared to higher frequencies. But because it is open to everyone, it quickly became crowded with Wi-Fi networks, microwave ovens, cordless phones, and many other wireless gadgets. This was making the frequency practically unusable. If a wireless device stayed on one frequency in this busy part of the spectrum, it would constantly run into problems like dropped connections, interference, and garbled data. Bluetooth was developed by the Swedish telecommunications company Ericsson, and they made the technology available to use by anyone by forming a non-profit organization to manage the development and licensing of the technology. For this, we have a lot to be thankful for. Having a universal system to connect our devices solves so many headaches. The solution they came up with was pretty creative: frequency hopping. Instead of staying in one spot, Bluetooth devices jump rapidly between different channels many times per second. That way, even if one channel was noisy or blocked, the device would quickly move to a clearer one before any serious interference could build up. There are some variations as to how these frequencies are agreed upon. Early versions of Bluetooth agreed upon a set frequency interval to hop, but newer versions use adaptive hopping, where the main sender tests out the different frequencies to see which work best when the devices first connect. For all that communication to work, the Airpod needs an antenna to receive Bluetooth signals. If you look at the scan, you can see 3 faint stripes inside the stem. That's the antenna. But it's not flat like a classic PCB trace. It wraps around the inside of the stem. The antenna needs to be in the stem because the human head is surprisingly good at blocking 2.4 GHz Bluetooth signals. If the antenna was placed deeper into the ear canal, much of the signal would get absorbed. Instead, Apple uses the stem to push the antenna further away from the head to improve signal reception. But now the antenna has to live inside the small, tight space of the stem, and that created a new challenge. The strip of metal that forms the antenna is just 2 mm wide and only 10 microns thick. That's thinner than a human hair. At that size, it can't hold its shape on its own. In other consumer electronics, antennas can be etched onto a PCB, but that limits them to 2 dimensions. There isn't enough space in the Airpod stem for that. So Apple uses a clever workaround. They embedded the antenna onto the surface of an injection molded plastic cylinder. If you open an Airpod, you'll see this black plastic part, and the metal antenna is perfectly molded onto it, following its complex surface like it was painted on. The secret is in the plastic. It has a small amount of metal added to it. A laser can then engrave the exact shape of the antenna into small channels with a rough surface that exposes the additive. That groove is then electroplated, first with copper and then coated with gold for corrosion protection. The result is a strong conductive path that matches the 3D geometry of the molded part that would be impossible to create using traditional machining methods. The plastic doesn't just support the antenna structurally. Other components can be attached directly to it, like the cable that snakes around the stem to connect the antenna to the Bluetooth chip, the pressure sensor in the stem, and this small metal box. This is just one of the microphones inside the AirPods. Prying one open will reveal that the metal box is actually mostly empty space. On one side, you can see a circle with dots covering its surface, and on the other, you'll see the cables that attach it to the amplifier. These are so much smaller than the microphones in a knockoff AirPod. The knockoff uses a much larger disc, almost twice the size. This is an electret microphone. An electret is a permanently charged plastic that creates a built-in electric field. Inside the mic, this material sits next to a thin diaphragm. When a sound wave hits the diaphragm, it vibrates and moves relative to the fixed rigid back plate. That tiny movement happening inside the electric field creates small voltage changes that match the shape of the original sound. That's the mic signal. Electret mics are compact and affordable, and they don't need a lot of power, but they're not perfect. They're sensitive to temperature shifts, and the electric material can be inconsistent from unit to unit. It's hard to make electric mics smaller because shrinking the size also shrinks the electric material. That means less surface area and less charge, which weakens the electric field. With less signal to work with, the mic struggles with its signal-to-noise ratio. AirPods use a similar idea, but with a more modern approach. Instead of relying on the charged electric material, they use a standard capacitor setup built on a silicon chip. This structure, known as a MEMS microphone, has 2 conductive plates spaced just a few millimeters apart. One plate is fixed, the other is flexible. When sound waves hit it, the flexible part moves, slightly changing the distance between them. That change alters the capacitance, which is then turned into a voltage signal. From the outside, this is what the MEMS microphone looks like, a small 3mm sized metal box, but the actual microphone, where the recording of the sound happens, is even smaller, a quarter of the size of its casing. So how do you actually build something this small? At this scale, traditional manufacturing methods like milling or molding just won't work. That's where silicon wafer manufacturing comes in. This is the manufacturing technique used to build computer chips, but applied to a mechanical device. The goal is to build a tiny box using different materials stacked at different heights. To do that, manufacturers build it up, layer by layer, by either adding material or etching it away from the silicon wafer using photolithography. Photolithography is a process that uses light to transfer a pattern onto the surface of the wafer. A light-sensitive coating is applied, then exposed to UV light through a mask. The exposed areas are either hardened or washed away, depending on the type of coating. The process starts by creating the microphone membrane. First, a temporary sacrificial layer made of silicon oxide is added to the surface. Then, a thin layer of silicon nitride or polysilicon is deposited on top. This forms the diaphragm, a flexible membrane that will eventually respond to sound. Next comes the creation of the cavity beneath it. This is done through tiny access holes that let the etching solution reach the substrate. The result is a clean, hollow chamber that channels sound toward the diaphragm. Then, the silicon dioxide sacrificial layers are dissolved away. So, if the microphone itself is a lot smaller than the metal casing, why even include a covering to make the microphone bigger than needed? As sound pressure acts on the diaphragms, it needs a sealed back volume to act like an acoustic spring. A smaller back volume will increase in pressure quicker and result in a stiffer diaphragm, which will act like a high bypass filter, resisting lower frequencies that want to push the diaphragm in further. Apple didn't invent MEMS microphones, but their decision to use them in iPhones and AirPods has drastically increased production and reduced their price across the board. Their tiny size allows Apple to add more microphones, but why would you need more than one microphone? You'll see at the bottom of AirPods a small mesh that allows air to flow into a second microphone. When you speak, your voice reaches both microphones, but not at the same time. With just a few millimeters in separation, the chip can detect the 6 microsecond delay between your voice reaching each mic. That's enough to figure out where the sound is coming from and focus on it. Since it knows exactly how far apart the microphones are, the chip can compare each signal and reinforce your voice on calls. But it gets better. There's actually a third microphone hidden inside, and it's placed in a pretty unexpected spot, right in front of the speaker, inside your ear. Why would you put a mic there of all places? Well, this one plays a key role in noise cancelling. Noise cancelling, like all my favorite things in life, was originally developed for aviation. Originally developed in the 1950s to cancel out the steady hum of the engine. Since that hum was steady and predictable, it was easy to cancel. Microphones on the outside of the pilot's headset picked up the engine noise, and the system created a sound wave with the opposite phase. When the two waves met, the noise vanished. This is a feed-forward approach, where the noise is measured first and then cancelled out with an inverted signal. But there's another way to cancel out unwanted noise, a feedback approach. The AirPods already know what the audio is supposed to sound like. By placing a microphone near your ear canal, they can measure what you're actually hearing. The system can then compare the intended sound with the real sound in your ear and constantly adjust to close the gap. It's a live feedback loop that works in real time to keep the noise out. There is a problem though. Those mics use around 130 microamps of current, which would drain the battery quickly if they were always active. That's why they only turn on when you're making a call or using noise cancellation. But AirPods are always waiting for a Siri request. How is that possible without having the microphones constantly active? If you look closely at the scan of the AirPod, you'll see a clever workaround. There's a small sensor tucked inside the part that is inside your ear, an accelerometer. It's the type of sensor used in phones to detect orientation, but here it serves a different purpose. Instead of measuring orientation, it feels for vibration. When you speak, your voice travels through your jawbone, and that vibration is picked up by the accelerometer. This low power signal is enough to wake the system and trigger the microphones when it senses you want to activate Siri. And of course, what's an earphone worth if the sound quality from its speakers suck? One of the defining features of AirPods are the black meshes inside the earpiece. They aren't just decorative or protective, they serve a surprising role in audio quality. Human ears are very perceptive to small changes in audio that you may not be aware of. The cartilage around your ear, called pinna, varies the sound coming into your ear in small but very perceptible ways. Remove those cues and things don't quite sound the same. Dogs don't have them, and that's why they have to tilt their head when they hear a sound. They need to create a vertical separation between their ears to detect vertical direction. Our ear pinna does that automatically. So, the design challenge is that a sound from 1 meter away can't simply be reproduced and shoved into your ear canal. And you notice this. Cheap earbuds without proper acoustic design nearly always sound worse. Apple has been designing earphones with this in mind since the very first wired earbuds. They have patents on acoustic models of the ear and on the design of the earbud itself, dating back to the early 2010s. One of the key references used in acoustic modeling is something called the Harman target curve. It's a benchmark for what good sound generally feels like to most people using headphones. It has a bit of a boost in the bass, a dip in the mids, and a slight rise in treble. The challenge is to create an environment that mimics this curve. Sound waves don't behave neatly. In a space as small and complex as your ear canal, they bounce and reflect and interfere to add up or cancel out. And since every ear is shaped a little differently, the resonances aren't the same from one person to the next. Ears naturally boost certain frequencies, which can lead to loud resonances. To keep that under control, precise ports, vents, and acoustic meshes are placed to allow the air to come in and out of the speaker. These meshes are carefully sized and placed to prevent those unwanted resonances from building up inside the ear canal. If certain frequencies are getting too sharp, the mesh geometry can help tone them down. A larger, more open mesh lets higher frequencies pass through more easily, while a finer mesh acts like a low-pass filter, letting most of the lower tones in and out of the Airpod. It's all about controlling airflow and pressure, making sure the sounds stay consistent and clean. But adding holes creates another problem: water and dust. If a vent is open to the outside world, it's also open to rain, sweat, pocket lint, and dust. That's where the hydrophobic meshes come in. Apple first used these in earlier iPhones to protect microphones and speakers. These meshes have a nano coating that repels water, but still allows air and sound to pass through. That technology was adapted for AirPods, letting the system stay acoustically transparent while sealing out moisture and debris. So the vent can do its job acoustically without risking damage to the internal parts. Thank you for watching this video on Nebula. Your support here helps us keep improving and investing in our craft.